So now that we've learned a little bit about transformations, it begs the question, is every possible transformation that we could think of, is every one of those going to be an acceptable change of coordinates? And the answer is, well, yeah, I'll just give it away. The answer is no, and let's see an example of why that's true. So suppose I define this transformation. So I say, let's let t of uv be the transformation defined by x equals u over u plus v, and y equals u over u minus v. Okay? As far as functions go, these things are perfectly fine. They're both undefined at the origin, so that's going to be an issue at the u and v equals 0. But what if we stay away from the origin? So we find like some rectangle that doesn't enclose the origin and ask ourselves, would this be acceptable? Can we use this to help us integrate? Well, to be able to integrate, we'll see as we move forward, we definitely need to be able to compute this area, right? So what happens to the area? And in the last video, I showed you that the area in the xy plane is equal to this thing called the Jacobian, J of uv, times the area in the uv plane. And this just means du dv. Okay, but the key here is the Jacobian. The Jacobian tells us how to scale the area. Okay, so let's compute the Jacobian of this thing and see what happens to it. So remember, to compute a Jacobian, we start with the matrix Jacobian, the j hat. And this thing is built by taking the partial derivatives, dx by du, dy by du, dx by dv, and dy by dv. Since these functions are a little more complicated, let's just take the derivatives separately and then we'll put them back together. Maybe we'll need another page to be able to do that neatly. But let's compute. So dx by du, this is going to be a quotient rule. So this is u times v times the derivative of u, which is just 1, minus u times the derivative of the lower, and then all over u plus v squared. So this simplifies to v over u plus v quantity squared. And then we can take dy du, same deal. This one's also going to be a quotient rule. So this is u minus v minus u times the derivative of the bottom with respect to u, so that's just 1, over u minus v squared. And this simplifies to be minus v over u minus v squared. All right, and then we move over to the next derivative. So dx dv, this one's going to be, so the v derivative, this is just a chain rule. So this will be minus u over u plus v quantity squared. All right, and dy dv, same deal, chain rule, but this time the v derivative, so it's going to be minus u over u minus v quantity squared times a minus 1 from the v derivative down there. Okay, by the chain rule. All right, and so this matrix then is given by, we can just very carefully write this out, it's v over u plus v squared, negative v over u minus v squared. And then the next column is negative u over u plus v squared, and then positive u over u minus v quantity squared on the bottom. All right, so this is the Jacobian matrix, and what we need to do next is take the determinant of this thing. So I'm going to copy this to the next page so I have room to write and it doesn't look too cluttered. So there's that. Right in the middle, of course. So let's move it up here. There's our Jacobian matrix. Now what we want to do is take the determinant of this thing. So our Jacobian function, j of uv, this is the determinant of the j hat matrix, which remember, the matrix, the other notation for the matrix was partial of what looks like a point xy with respect to uv. Okay? But remember how the determinant works. You take the products of the diagonals and then you subtract them, right? So the main diagonal, the product is going to be u times v over this denominator, which is u plus v squared times u minus v squared. And then we subtract off the product of the off diagonal, the red diagonal here. This has 2 negative, so that's going to be positive on top, but we're subtracting it. So minus uv over, and this is the denominator is the same, right? U minus v squared. And so then we notice these two things are the same, so this Jacobian is 0. So what does that tell us? Well, this tells us that this transformation takes a rectangle in the UV plane, our tiny little 1 by 1 rectangle in the UV plane, right? So, and we can even avoid the origin to make sure that it makes sense, and it maps it to something that has no area in the XY plane, no two-dimensional area. So we know that it doesn't map to a point, so what it must do is it must collapse both of these edges into the same single direction. Maybe it looks like this over here. And so the area in this space, area is equal to 0. And of course, that's not going to be an acceptable transformation if we're trying to do a double integral over an area element if this thing has 0 area. Okay? So the conclusion here is that if the Jacobian of our transformation is equal to 0, then it cannot be an acceptable coordinate transformation, change of coordinates. We'll just write it is not acceptable. All right, and this is the key. If the Jacobian is 0, it means it collapses a two-dimensional shape into a one-dimensional shape, or maybe even just to a point. Either case, that's bad. Okay, that's bad.